Hey everybody, and welcome to another deep dive. Today we're tackling a topic that never fails to get people talking.
Oh, yeah.
The shape of the Earth. Flat Earth versus spherical Earth.
I know, right?
We got a whole bunch of arguments from both sides.
Mm-hmm.
So let's jump right in and see what we can uncover.
Sounds good.
Let's start with the flat Earth theory.
Okay.
One of the things they always bring up is that if you just look around, it seems like the horizon's flat.
Right.
Like when you're at the beach looking out at the ocean.
Yeah, you stand there and think, maybe they're onto something.
Exactly.
Mm-hmm.
So how do we explain that if the Earth is actually a sphere?
Well, it all comes down to scale.
Scale.
Yeah, the Earth is so incredibly huge.
I mean, yeah, it's big, but
It's way bigger than we can really grasp. So from our perspective, down here on the surface,
okay.
that curve is so subtle it just looks flat.
That's
Like imagine an ant on a giant beach ball. It'd look pretty flat to that ant.
That's a good way to put it. So it's all about perspective. But what about those experiments that some people say proved the Earth is flat?
Oh, you mean like the Bedford level experiment?
Yeah, that's the one.
Yeah.
They measured this stretch of water and said it was totally level, no curve at all.
Right, right.
That seems like pretty convincing evidence, doesn't it?
Well, it did cause a lot of debate back then, but when scientists looked into it more closely, they found some problems with the way the experiment was set up.
Like what?
You got to factor in things like atmospheric refraction, which is how light bends as it goes through the air.
Huh.
That bending can really mess with how we see distances and make things look flatter than they really are.
So it's like a mirage.
Kind of, but for straight lines instead of shimmering water.
Wow, that's crazy. But okay, what about all those pictures we see from space?
You mean the ones showing the Earth as a big blue sphere?
Yeah, those?
Yeah.
Flat Earth folks often say they're fake.
Right.
It all feels a bit conspiracy theory sometimes.
I get that, but think about it. We have images from so many different sources. Like, tons of countries have their own satellites taking pictures.
True.
And they all show the same thing around Earth.
I guess it would be a pretty big conspiracy to fake all of that.
It would be a massive undertaking.
Okay, so if we can't trust pictures from space, what about flight paths?
Flight paths.
Yeah. Some people say certain airline routes make more sense on a flat Earth map.
Oh, I see what you mean.
Like they look more direct, cutting straight across instead of going around a curve.
That's an interesting point.
Sometimes when I'm looking at a flight tracker, I think, wait, that doesn't seem right.
Well, remember, any flat map is just trying to represent a 3D object on a flat piece of paper.
Yeah.
You can't do that without distorting things.
Right.
Different map projections emphasize different things,
Yeah.
which changes how distances and routes look.
So those straight lines on a flat map might actually be curves on the real Earth.
Exactly.
It's like those orange peel maps they show in school.
Uh-huh. Yeah, you can't flatten an orange peel without ripping it or stretching it weird.
So maybe those flat maps are giving us a false impression.
It's possible. Now, this next flat Earth argument is one of my favorites.
Oh, let's hear it.
They say Antarctica is actually a giant ice wall surrounding the edge of the world.
Whoa. That sounds like something straight out of a fantasy novel.
It does, doesn't it? Like a massive wall of ice guarding the edge of reality.
It's an awesome image, but is there any truth to it?
Well, we've done a lot of exploring in Antarctica.
Mm-hmm.
There are research stations all over the continent, and scientists have gone on expeditions all across it.
So you're saying if there was a giant ice wall, we would have found it by now?
I think it would be pretty hard to miss.
I guess that makes sense. But okay, let's talk about something even more mysterious.
More mysterious than a giant ice wall.
Way more. Gravity.
Ah.
Flat earthers often say that gravity, as we understand it, doesn't exist.
And what do they say instead?
They claim it's all about density and buoyancy, not some invisible force pulling things down.
I've heard that one before.
Like a rock sinking in water, because it's denser.
Right, but that doesn't explain why gravity affects everything the same way no matter how dense it is.
Oh yeah, good point.
If you dropped a bowling ball and a feather in a vacuum, they'd fall at the exact same speed.
Right.
Because gravity's acting on them equally.
So it's not just about things sinking or floating.
Exactly. It's a force that affects everything equally.
But hold on, if the Earth is round and gravity pulls everything towards the center,
Yeah.
wouldn't people on the bottom of the Earth be upside down?
Yeah.
And wouldn't everything fall off?
That's a common misconception.
Is it?
Yeah, we tend to think of down as one direction, but on a sphere, down is always towards the center.
Oh, wow.
No matter where you are on the surface, down is towards the center.
I never thought about it like that.
So people on the other side of the Earth feel perfectly normal.
Because their down is towards the center, just like ours.
Exactly.
Mind blown. So it's like the Earth is hugging everything to its surface.
I like that analogy.
Okay, but flat earthers also talk about being able to see things that should be hidden by the curve.
What do you mean?
Like seeing a lighthouse that's supposedly too far away on a round Earth.
How do they explain that?
That's where atmospheric refraction comes in again.
Ah, right. Remember how light bends in the air?
Yeah.
Sometimes the layers of air can act like a lens bending light downwards, and that lets us see things that should be hidden by the curve.
It's like that thing where a straw looks bent in a glass of water.
Exactly.
So the air is playing tricks on us.
It can definitely mess with our perception.
Okay, one last flat earther point before we move on.
Okay, shoot.
They often talk about star patterns, especially how Polaris, the North Star, seems to stay fixed in the sky.
Yeah, Polaris.
If the Earth is rotating, shouldn't it be moving?
That's a great question. It seems counterintuitive, but the reason Polaris looks stationary is because of the Earth's tilt.
Tilt.
Yeah, the Earth's axis, the line it spins around is tilted.
Right.
And Polaris just happens to be almost directly above the North Pole. So as the Earth spins, Polaris stays in roughly the same spot, while other stars appear to circle around it.
Wow, so Polaris staying put actually supports the idea of a rotating tilted Earth.
Exactly. It all comes down to geometry and perspective.
That's incredible. It's like a giant cosmic dance, and we're down here watching it.
That's a beautiful way to put it.
So we've explored some of the key arguments from the flat Earth side.
Some really interesting points.
Now let's shift gears and dive into the evidence that supports a spherical Earth.
Okay, I'm ready for round 2.
Get ready for some mind-blowing science, because it goes way beyond just, we saw it from space.
Sounds good. Let's do it.
I can't wait to uncover more clues about the shape of our amazing planet.
Me too. This is going to be fun.
Okay, so we've spent some time with the flat Earth folks, but now let's switch gears and dive into the science behind a spherical Earth.
Yeah, let's get into it.
Because there's so much more to it than just, it looks round from space.
Right. There's a ton of evidence from all sorts of different areas.
Exactly. So let's start piecing together this spherical puzzle.
Sounds good.
One of the things that always gets me is the classic ships disappearing hull first thing.
Oh, yeah, that's a classic.
You know, you're standing on the beach and a ship sails away. And it doesn't just get smaller, it starts disappearing from the bottom up.
Like it's sinking beneath the waves, even though we know it's not.
Right. It's kind of spooky when you think about it.
It is. And it's a really clear sign that the Earth is curved.
So how does that work exactly?
Well, imagine you've got a big beach ball in front of you.
Okay.
And you start walking away from it.
Uh-huh.
The bottom of the ball will disappear from your view first, right?
Yeah, I guess so.
And then the top will still be visible for a while longer.
I see.
That's because the curve of the ball is blocking your view of the bottom.
So it's the same thing with ships and the Earth's curve.
Exactly. The Earth itself is getting in the way.
Wow, that's so cool. It makes you realize that what we see isn't always the whole story.
Absolutely. Our perspective can really shape how we perceive the world.
Okay, now let's talk about something else that's always fascinated people. Lunar eclipses.
Oh, yeah, when the Earth's shadow falls on the moon.
Right. And the moon turns this creepy shade of red.
It's pretty amazing to see.
But it's not just a cool visual spectacle. It's also evidence for a spherical Earth.
You got it. Think about it. The Earth casts a round shadow on the moon no matter where the moon is in its orbit.
That's true.
If the Earth were flat, the shadow would look different depending on the angle of the sun.
Like it might be stretched out or something.
Exactly. But we always see a circular shadow.
Which means the Earth has to be round.
It's like the universe is giving us a clue with those eclipses.
I love that. Speaking of clues from the sky, have you ever noticed how the constellations change as you travel north or south?
Oh, yeah, definitely. Like if you go to Australia, you'll see a whole different set of stars compared to here.
Right. It's like you're unlocking new levels of the night sky.
I like that analogy.
Yeah.
And that happens because of the Earth's shape and its tilt.
Yeah, remember, the Earth's axis is tilted.
Oh, right.
So as you move north or south, your view of space changes.
So it's like we're on a giant spinning merry-go-round and our view keeps shifting.
That's a great way to visualize it. It's amazing to think that our ancestors used those stars to navigate across oceans.
Yeah, way before GPS. Okay, now let's circle back to gravity for a second.
Back to gravity.
Yeah, because it's not just about things falling down, it's also evidence for a spherical Earth.
Right, so how does gravity play into this?
Well, we know it pulls everything towards the center of the Earth. But how does that prove the Earth is round?
Because on a sphere, every point on the surface is the same distance from the center.
Oh, I see.
That means gravity pulls equally on everything no matter where you are.
Okay.
But if the Earth were flat, Gravity would pull things differently depending on your location.
How so?
Well, think about it. On a flat plane, the strongest pull would be towards the center.
Hmm.
And the further away you got, the weaker the pull would be. So things would feel heavier in the middle of a flat Earth.
Exactly. But we know that gravity is pretty much the same everywhere.
Which means the Earth must be a sphere.
It all fits together.
Okay, now let's talk about something a bit more adventurous. Circumnavigation.
Circumnavigation, those epic voyages around the world.
Exactly. Sailing all the way around, proving that you can keep going in one direction and end up back where you started.
It's one of the most convincing proofs of a spherical Earth.
Because on a flat Earth, you'd eventually hit an edge, right?
Or fall off.
Haha. Yeah, I wouldn't want to test that theory. It's incredible to think about those early explorers setting off into the unknown.
They faced so many dangers just to prove that the Earth was round.
Their courage and determination paved the way for so much of our understanding today.
Absolutely. But even before those epic sea voyages, there were some pretty clever folks figuring things out right here on land.
Oh yeah, like
Have you ever heard of Eratosthenes?
Eratosthenes. That rings a bell.
He was this ancient Greek guy who calculated the Earth's circumference using just sticks and shadows.
Wait, really? How did he do that?
He noticed that at noon on the summer solstice in a city called Syene,
Huh?
the sun shone straight down a well with no shadow.
No shadow.
Yeah. But in Alexandria, a city further north,
Okay.
a vertical stick cast a shadow at the same time.
Interesting.
By measuring that shadow's angle and knowing the distance between the two cities,
Yeah.
he was able to calculate the Earth's circumference.
That's amazing. Just using shadows and some geometry.
It's a testament to the power of observation and deduction.
It makes you wonder what other secrets are hidden right in front of us, just waiting to be discovered.
That's the beauty of science. There's always something new to learn.
Okay, now let's shift our focus to the skies again this time, to satellites and space stations.
Okay. Those are always fun to talk about.
They're constantly orbiting the Earth, sending back incredible data and images.
And their orbits are only possible because the Earth is a sphere.
Oh, how so?
Well, think about it. A satellite is basically falling around the Earth.
Falling.
Yeah, it's moving so fast horizontally that it keeps missing the ground. And that curve that it follows is determined by the Earth's shape and gravity.
So if the Earth were flat, satellites would either fly off into space or crash back down.
Exactly. It wouldn't work.
So they're constantly falling but never hitting the ground. That's wild.
It's like a cosmic dance between gravity and velocity.
I love it. Okay, now let's bring things back down to Earth, literally with time zones.
Time zone. Yes, those things that make international travel so confusing.
Yeah, but they're also a direct result of the Earth being a rotating sphere.
You got it. As the Earth spins, different parts of the planet face the sun at different times.
Right, which is why it's morning in one place and evening in another.
Exactly. But if the Earth were flat, the whole surface would experience day and night at the same time.
So it would be like one giant time zone.
Pretty much, yeah.
Can you imagine trying to schedule meetings across a flat Earth?
It would be chaos.
Let's meet when the sun is sort of halfway up the sky over your house.
Yeah, good luck with that. Time zones, as confusing as they can be, are proof that we live on a rotating sphere.
Okay, and speaking of things affected by the Earth's rotation, let's talk about the Coriolis effect.
The Coriolis effect.
Yeah, it's this thing that makes things spin in different directions depending on which hemisphere you're in.
Oh, yeah, like hurricanes spin one way in the north and the opposite way in the south.
Right. So what causes that?
Well, it's all because the Earth is rotating.
Okay.
Points on the Earth's surface at different latitudes are moving at different speeds. And that difference in speed creates this apparent force that deflects moving objects.
So it's like the Earth's rotation is pushing things off course.
In a way, yeah, it's this invisible force that's constantly at play.
That's so cool. It makes you realize that even the smallest things are affected by the Earth's movement.
It's all connected.
Okay, and last but not least, let's talk about one more piece of evidence that demonstrates the Earth's rotation. The Foucault pendulum.
The Foucault pendulum, a classic.
I've seen those in museums, a giant pendulum that swings back and forth.
Yeah, but the cool thing is that the direction of the swing slowly changes over time.
Right, it looks like it's rotating.
And that rotation is actually proof that the Earth is spinning beneath it?
Wait, so the pendulum itself isn't rotating?
Nope, it's the Earth that's moving.
Whoa, that's trippy. It's like the pendulum is holding still and the Earth is spinning under it.
It's a mind-bending concept, but it beautifully illustrates the Earth's rotation.
It's like a giant clock keeping time with the Earth's spin.
Exactly. And it reminds us that we're not just standing still on a planet, we're part of a dynamic system that's constantly in motion.
Wow, what a journey we've been on, from ships disappearing to pendulums that defy intuition.
It's amazing how all these different pieces of evidence point towards a spherical Earth.
It really shows the power of scientific inquiry and how we can piece together a picture of the world around us.
It's a beautiful tapestry of knowledge woven from observations, experiments, and human curiosity.
But even though we've explored all this evidence for a spherical Earth,
Yeah,
do you think there's anything we can learn from the flat Earth perspective?
absolutely. Even though their model is scientifically inaccurate, they make us think critically about what we believe and why.
It's like a reminder to always question our assumptions.
Exactly. Science is all about constantly exploring, questioning, and refining our understanding of the universe.
So it's not about being right or wrong. It's about being open to new ideas and searching for the truth.
Couldn't have said it better myself.
So we've gone on quite the adventure, haven't we? From questioning the horizon to uncovering ancient experiments to launching ourselves into orbit with satellites.
It's been quite the journey exploring all these different perspectives.
Yeah, and we've seen some really compelling arguments from both the flat Earth and the spherical Earth sides.
Both sides make you think.
But after all this exploration, where do we land? What's the takeaway?
Well, for me, the beauty of science is that it's about following the evidence wherever it leads. And in this case, all that evidence from the curvature of the horizon to the way things move in the sky, it all points towards a spherical Earth.
So the spherical Earth model is the one that best explains all these observations.
Exactly. It just fits together so elegantly, explaining so many different things.
It really shows the power of human curiosity, doesn't it? Our drive to understand the universe.
Absolutely. It's incredible what we've been able to learn about our planet.
From its shape to its movements to the forces that govern it.
It's a testament to centuries of scientific exploration.
But even with all we've learned, there's still so much more to discover.
Oh, yeah. Definitely, the more we learn, the more we realize how much we don't know.
Exactly. It's like every answer opens up a dozen new questions.
That's what keeps science so exciting.
Okay, before we wrap up, I want to leave our listeners with a thought-provoking question.
Okay, I like where this is going.
Imagine for a moment that the Earth actually were flat.
Okay, I'm imagining.
What other things about our understanding of the universe would have to change?
Whoa, that's a big question.
Like, what fundamental laws of physics would need to be rewritten?
Well, for starters, our understanding of gravity would have to be completely different.
Right, because gravity pulls everything towards the center of a sphere.
Exactly. And if the Earth were flat, gravity would have to work in a totally different way.
And what about the stars and planets?
Yeah, the whole model of the solar system and the universe would need to be reimagined.
It's like we'd have to rip up the cosmic rulebook and start over.
It's mind-boggling to think about.
It makes you appreciate how much our current understanding of the cosmos relies on the fact that we live on a sphere.
It really does. It shows how interconnected all of these ideas are.
So it's not just about the shape of the Earth, it's about how that shape affects everything else we know.
Exactly. It's all part of a bigger picture.
Well, I think that's a great place to leave it for today.
Yeah, it gives everyone something to ponder.
Thanks for joining us on this deep dive into the flat Earth versus spherical Earth debate.
It's been a pleasure exploring this with you.
Remember, keep looking up, keep questioning, and keep exploring the wonders of our world.
Because who knows what other amazing discoveries are out there waiting to be made.
Until next time, keep those minds curious.